Good morning, everybody. Welcome to overcast, somewhat light rainy Thursday morning of chemistry, Chem 1211, with your host, me, Dr. White. Ooh, wait, that's better. Ooh. And what are we going to do today? Well, we've done all the problem sets, but I thought to help you out, I can go back and do a couple of things, and then we'll do the lab, and you'll get out early today, which are all going, yay. I guess I can go yay too, but I don't want to cheat you out of your time. But if we were face to face, we do the same thing. You get out early. All right, let's go back to some problem sets. That's not what I want. That's what I want. All right, thumbs up, people. Do you see chapter 6 on your screen? Thank you. All right, remember, a mole is a counting unit, chemist counting unit. Would I have that, ask that on a test? I did, test number 2. And what's Avogadro's number? 6.02 times 10 to the 23rd. Which reminds me, I should open up the following. Everybody see 1 mole equals on your screen? Oh no! Now do you see it? 1 mole. Thank you. Thank you, Gabby. I guess you're the only one with your monitor on. So it's just you and me and some other names here today. All right. These are 5 things you should know. This will be an important information, the final exam. 1 mole of an element equals Avogadro's number of atoms of that element. 1 mole of a compound equals Avogadro's number of molecules of that compound. And 1 mole of an element equals the atomic weight of that element in grams. And 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of a compound, tea break, is equal to the sum of all atomic weights. And if we go back and look at number 3, I better ask, everybody see number 3 on the screen? Thank you. It asks how many atoms are 6.574 moles of sodium. We're trying to get atoms of sodium. We're given moles. And it's time to use, oh, I haven't done this in a long time. It's time to use your good buddy, your good friend, unit analysis. I love that whistle. And it is. And hopefully by now you've seen it is your good friend and your good buddy. And here's what we have to start with. What are we trying to get to? Atoms of sodium. So whatever we're trying to get to, we put the units on top of a ratio. Whatever we're trying to get rid of, we put on the bottom of the ratio. Where do we get these numbers? Remember, when 2 things are equal, you can have 2 ratios. Where do we get a relationship between 1 mole, in this case of sodium, an element, and the atoms in a mole? If we look here, 1 mole of an element equals 6.02 times 10 to the 23rd atoms, Avogadro's number of that element. All right, Zoom is playing games with me. Everybody see the problem now again? I'm going to have to ask more. I apologize. But so 1 mole equals Avogadro's number. On the final, like all our tests, underneath your name, one of the things we'll say is please use proper significant figures for all calculated answers. And if you don't, I take off a point like I've done all semester. And notice this is 4 significant figures, 3. The 1 is part of the definition. It's the exact number. When you do multiplication and division, you get the same number of significant figures in your answer that the number you're using, multiplying or dividing, that has the fewest significant. This is 4, this is 3. My answer is 3 significant figures. And that's how you do it. You know something? Actually, don't know something because you can't read my mind. Hold on, I see a question. Biljana, this is from chapter 6. And as always, all questions are good questions in my universe. All right. And why don't you try this one? And it reads, how many moles, this will probably be 5 or 6 points, how many moles HCl are 5.55 times 10 to the 25th molecules of HCl? If you haven't figured out by now, Dr. White loves numbers that are 5 or multiples are 5. Don't ask me why, but I do. And don't forget, 1 mole of a compound equals Avogadro's number of molecules of that compound. And when you're done, give me a thumbs up. Those of you who don't have your camera on, use the symboli. Remember, I'm no longer using emoji. I've changed it to symboli. All right, looks like everybody's done. Let's do this. What are we being asked to find? Moles of HCl. What are we given? these many molecules of HCl. This is the only number we have to start with, so I'm going to start with it. And now, if I could convert this in one step, what units do I want my answer in? And that's moles of HCl. And now it's time to use your good buddy, your good friend, unit analysis. And whatever we're trying to get to, we put the units on top of this ratio. Whatever we're trying to get rid of, we put it underneath. That wasn't hard. And where do we get these numbers? 1 mole is equal to 6.02 times 10 to the 23rd molecules of HCl. Notice molecules of HCl over molecules cancel out because anything divided by itself equals the number 1, and we're left with the units we want. So now I can happily go to my calculator, but first let me write down the number. I might forget it. And let's open up our calculator, which we haven't used in a while. Thumbs up, people. You see the calculator? No. Oh, no. Hold on. Zoom's telling me you should, and you're telling me the truth. Now do you see it? All right. Like I said, Zoom is being mean to me today. You know, software can be nice or mean to you. And that's the number I get. Now, both were 3 significant figures, and I'm going to let you round that off to 3 significant figures, then I'll do it. Time's up. Keep the 9, keep the 2, keep the 1. Those are my 3 significant figures. Use the 9 to round off. So that 4 or less or 5 or higher. And time's up. It's 5 or higher. So I'm going to drop that, change the 1 to a 2. And that would be 9.22 times 10 to the 0, which is 9.22. If you put down 10 to the 0, I'll smile, but I'll never mark it wrong. So the answer for that problem is 9.22 times 10 to the 0, or 9.22, because 10 to the 0 equals 1. And that's how you do it. Let's move on. All right, let's look at number 14. Everybody, can you see number 14? Thank you. This is going to be Ask a Lot morning. All right, what's the molecular weight of sulfuric acid? And how do you do molecular weight? The molecular weight is the sum of all atomic weights, and therefore we look at H2SO4. By the way, I hope you know that's an acid. We went through that in the acid-base chapter. 2 hydrogens, 1 sulfur, 4 oxygen. And as you remember, maybe you don't, I better open this up too. All right, everybody see the periodic table? Thank you. Well, how do you find the atomic weight of a compound? Well, first of all, you make this periodic table larger so you can see. You look underneath the compound and you see the atomic weight. Hydrogen is this, oxygen is over here. And on the final, like test 2 and 3 and 4, it will say under your name, please use 3 significant figures for all atomic weights. For hydrogen, that'd be 1.01. For sulfur, that would be 32.1. And for oxygen, that'd be 16.0. Have you noticed I have 2 hydrogen, now 2 times 1.00, 1 sulfur, 1 times 32.1, and 4 oxygen, 4 times 16.0. The bracket fell off, so just imagine it's there. Do the math. You get these 3 numbers added up. Now, remember, when you do addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. Everything on the left you leave alone, you just add. And here 2, 1, 1, and therefore the second dot shouldn't be there. I don't know how it got in there. But anyways, 98.12 rounded off to 1 past the decimal. Keep the 1, use the 2 to round off. That's 4 unless I drop it, is 98.1. And why don't you try this one? What's the molecular weight of water? And this is in case you don't have your periodic table handy. Hydrogen has atomic weight of 1.01 to 3 significant figures, oxygen 16.0. And hopefully none of you are suffering from Zoom fatigue. And give me a thumbs up when you're done. Well, I guess people are still working. I'll give you another 10 seconds. Hurry up. All right, let's do it. How do you do the molecular weight of water, H2O? It's the sum of all atomic weights. There are 2 hydrogen and 1 oxygen. I put the dash there so you know I'm not writing the number 10. That's 2. And what's the atomic weight of hydrogen? The 3 significant figures. this. What's the atomic weight of oxygen? To three significant figures. It's this. Do the math. Remember, these are exact numbers. Now, when I add these up, I have 18.02. Notice this has 1 past the decimal. This has 2, which is the lower number. I hope you all pick 1. So I keep the 0 and use the 2 to round off. It's 4 or less. So the correct answer is this. Now, let's look at number 15. Hopefully number 15 is on your screen right now. Everybody see them? Thank you. How many moles are 34.56 grams of water? We're trying to find moles of water. We're given grams of water. And what do? Well, first of all, we go to important information. The final exam I have up here, test number 2, but this will also be the final exam. 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So I'm trying to find moles of water. I'm given grams of water. This is what I have to start with. What units do I want my answer in? Moles of water, right here. So using your good buddy, your good friend, unit analysis, whatever you're trying to get to goes on top. Whatever you're trying to get rid of goes underneath. Where do you get these two numbers? 1 mole of a compound water equals its molecular weight, which we just figured out, and I have it here again, 18.0. Notice this is 4 significant figures, 1. This is 3 significant figures, and my answer is 3 significant figures. Now, we just did a problem. I showed you that the molecular weight, H2SO4, which I showed you how to calculate, is 98.1. So I'm going to give it to you in real world. You'd have to calculate it, and it's your turn to have some fun. Have fun. That's an order. Yeah, hopefully you've all enjoyed my videos this semester. I'm still trying to figure out the secret final chapter surprise ending. And for those of you who came in late, I gave the winning lotto numbers for the end of the week, so you missed out on all that. You didn't know Dr. White can see things in the future. Actually, I have ESPN and I also have ESP. Throughout my life, I've said things in jest, and somebody says, "How did you know that?" And it always scares me when I do something like that. I don't know. My brain works at a special level. Now, if I could just figure out what level that is. It's totally nonsensical humor Thursday, and you've got to suffer through it along with me. If you're done, give me a thumbs up. All right, those who are giving thumbs up just did. Let's do it. What are we being asked to find? Grams of H2SO4. What are we given? 3.33 moles of H2SO4, sulfuric acid. This is the only thing we have to start with, so I will. What units do I want my answer in? Well, we figured that out. Grams of sulfuric acid. And now it's time to use your good buddy, your good friend, and it's been mine for many decades. Oh, no, I shouldn't have said that. Makes me feel old. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath the unit wise. And with that, I have grams of sulfuric acid and mole of sulfuric acid. And where do I get these numbers? 1 mole of a compound equals its molecular weight, which previously we figured out was 98.1. And notice 3 significant, 3. The 1 is part of the definition. That's the exact number, doesn't play a role in there in the final determination of significant figures. Therefore, I should have 3 significant figures. And now I'll go to my calculator. And this is the number I get. Or if I went to my one with the scientific, and if you look on A1 here in yellow, that should be 3 significant figures. I'll let you round that off. Time's up. Keep the 3, keep the 2, keep the 6. That's my 3 significant. Use 6 to round off. That's 5 or higher. Drop that, change the 6 to a 7. So my answer is 3.27 times 10 squared. And that's how you do it. And let's continue on. For those who came in late, since we don't have any problem sets, I figured I'd do something that's a good review for all of you. Oh, that rhymes. All right, now, if you look at Chapter 8, Practice Problems, and here we've got something more sophisticated. We have a balanced chemical equation, and the question is, how many moles of oxygen are needed to make 23.33 moles of CO2. And how do we do that? We have moles of oxygen we're trying to find. We're given moles of CO2. Use your good buddy, your good friend, unit analysis. And here we say, here's what I'm starting with, moles of CO2. I want to get the moles of oxygen. If I could do this in one step, whatever I'm trying to get to goes on top of the ratio, moles of oxygen. Whatever I'm trying to get rid of, moles of CO2 go underneath. And where do we get this information? From the balanced chemical equation. Remember, the coefficients give you molar ratios. One, and when there's no number, it's the number one. Coefficient number in front of the atom or molecule in a balanced chemical equation. And this tells me I have 1 mole of C3H8 propane, the stuff you buy in that white tank, plus 5 moles of oxygen, make 3 moles of CO2 and 4 moles of water. Again, tea break. 1 mole of propane, C3H8, reacts with 5 moles of oxygen to make 3 moles of CO2 and 4 moles of water. And therefore, here we have 3 moles of CO2. You need 5 moles of oxygen. We get it from here. These are exact numbers, 4 significant figures. I got a mistake here. That should have been 4 significant figures, but do the math and that's how you do it. Time out while I copy something down. All right, it's time for Dr. White to decode what I just wrote so you can understand it. Given that, everybody see the balanced chemical equation? Thank you. If you react 8.513 moles of ammonia, NH3, with an excess of oxygen, then how many moles of nitrogen will you make? And it's your turn. Don't forget to use your good buddy, your good friend, unit analysis. Aren't you glad I taught you that? I am. That's the secret reason my students do good. All right, if you're done, don't forget, give me a thumbs up. Uh-oh, no thumbs up, so you're not done. I see one person done. I was tempted to go on the internet and see if they've hung Liz Cheney yet. I hope not. I don't agree with her policy stance, but I agree with what she's doing now, and she's being a very brave person. Enough of politics. Let's go to fun things, chemistry. All right, everybody done? Let's do this. What are we being asked to find? Moles, nitrogen. What are we given? This amount of moles of ammonia. And we're also given this balanced chemical equation. So this is the only number I have to start with. I will. And if I can convert this in one step, what units do I want my answer in? Well, I figured that out. Moles of nitrogen. And now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of, unit-wise, goes under there. Let me write the units in. And where do I get a ratio of moles of nitrogen, moles of ammonia? Up here. For every 4 moles of ammonia, I make 2 moles of nitrogen. For every 4 moles, remember the coefficients, the number in front, give you molar relationships. For every 4 moles of ammonia, I use 2 moles of nitrogen. And notice moles of ammonia cancel out because anything divided by itself equals the number 1. And I get the right answer unit-wise. So now I can go to my calculator and go and this is the number I get. Does everybody see my calculator? Okay. Now, the first number was 8.513 for significant figures. The 2 and the 4 are exact numbers. Therefore, you have to round this off to 4 significant figures. I'll give you 4 seconds. Time's up. I gave you more than 4 seconds, I bet. Keep the 4, keep the 2, keep the 5, keep the 6. Those are my 4 significant figures. Use the 5 to round off. Is that 5 or higher? And I hope you got it right. It is 5 or higher. So I'm going to drop that, increase the number in front of it, 6 or 7. So the answer would be 4.257 and moles of nitrogen. And that's how you do it. Remember, a balanced chemical equation gives you molar ratios. In this case, 4 moles of ammonia make 2 moles of nitrogen. We could have also, but not in this problem, 3 moles of oxygen would make 2 moles of nitrogen, and also makes 6 moles of water when it reacts with ammonia. All right, everybody see problem 4 on the screen? Thank you. All right, now let's put together everything we learned. And this is a real world example. And I've done these calculations to determine how much of various chemicals do you mix to make a product. And in real world, I've worked with, here we work in the lab with grams, but you can substitute pounds for grams. I work with numbers like 400, say 40, 50,000 pounds of a chemical. But let's look at number 4. You're given a balanced chemical equation. Hydrogen reacts with chlorine to make HCl. How many grams of hydrogen, H2, are needed to make 125.6 grams of HCl? Well, we can ignore chlorine because we're being not asked about that. What are we being asked to find? Grams of hydrogen. What are we given? Grams of the product, HCl. There's no way anyone can go from this number to the answer in one step. You need 3 steps. Where do you find those 3 steps? Good news, I'm no longer making people memorize everything, and that's mass calculations for reactions. The first step, whatever you're given in grams, meaning the mass, you convert to moles. We did that earlier today. Second step, whatever you have in moles now of what you just calculated, you go to moles of your answer. We just did that. And finally, we go from moles of what we just calculated to the grams of our answer, which we also did earlier today. Let's take a look at that. And here, step 1, we're given grams of HCl. We want to convert it to moles of HCl. Here are the grams. We want to go to moles, use the unit analysis. Moles HCl go on top of the ratio, grams go underneath. 1 mole of a compound equals its molecular weight. The molecular weight is the sum of all atomic weights. For HCl, hydrochloric acid, is 36.5. Due to math, 4 significant, exact number 3. This is the number we get. Second step, the moles of what we just calculated, this, we convert to moles of the answer we want to get. In this case, hydrogen. Here's what I have right here. Here's what I'm trying to get to. Moles of hydrogen goes on top. Moles of HCl go underneath. Where do you get those numbers? From your balanced chemical equation. For every 1 mole of hydrogen, I make 2 moles of HCl. For every 1 mole of hydrogen, I make 2 moles of hydrochloric acid. So for every 1 mole of hydrogen, I make 2 moles of HCl. These are exact numbers, 3 significant figures. My answer is 3 significant figures. Now, how do we go step 3? Step 3 is moles of what we just calculated. We convert to grams of that molecule, which is the answer we want. We're going from moles of hydrogen to grams of hydrogen. How do we do that? We use your good buddy, your good friend, unit analysis. And whatever I'm trying to get to goes on top, grams of hydrogen. Whatever I'm trying to get rid of goes underneath, moles of hydrogen. Where do I get these 2 numbers? 1 mole of a compound equals the molecular weight of that compound. The molecular weight is the sum of all atomic weights. 2 hydrogen, 2 times 1.01 equals 2.02. Put that in there, 3 exact number, and it's 3 significant figures. Now, if you notice on this one, I have or. Another answer, 3.48. What does that mean? It means I'm not going to force you to do what I like to do. And what am I talking about? There are two philosophies when you're doing multiple step calculations. One is you round off at the very end. The other is you round off at each step. I am a round off at each step person. But if you want to do it at the end, I'm not going to force you to do it my favorite way. And therefore, I will always on a problem, and you've seen that's a semester, calculate things both ways, here and here. And that's how you do it. All right. Public service announcement from Dr. White. That's me. And that is what's going on next week. And I should have mentioned this yesterday, but I forgot to. Bad, Dr. White. But I can do it now and also tomorrow. And that is next week is review. And it's really important. Show up because I'm going to go through stuff and it will help you for the final exam. Now, on Monday and Wednesday, we'll have our normal lectures and I'll do reviews. And I would highly recommend it. Now, if we were face to face, Thursday in lab would be checkout. And in the lab, when we work face to face, you work in pairs, groups of two, in case you forgot what pair is. And each pair has their own drawer of chemical equipment. And before we end the semester, my lab goes through and checks that all the equipment you started with, because you checked in, is there. If you're missing anything, I go to the stockroom and replace it. Well, after doing this a while, I realized it's a lot quicker if I just go around and do it myself instead of having the students. So I normally tell the students, you want to stop by, say hello to Dr. White, you can. If not, I'll be there only for a half hour and I'm out of there and you don't have to show up. And that's standard. But since we're doing Beyond Lab Z, you don't have to show check out. But what I will be doing, which is a good thing, is I will be doing on Thursday and Friday practice problems for the whole semester. If you want to show up, show up. If you don't, you don't. Now, what I'll tell tomorrow's group two is both of you had the same password for the same Zoom address, just on different days for your lab. So next week, show up on Thursday if you want to check out what I'm doing. And if you want, you can also come Friday. And that's that. And I look at the clock and it's time for our break. Let's take a 5-minute break, come back in 5 minutes, 9:55, and then we'll do our last lab. All right. Time to get back to work. Come out wherever you are. What was that? Oh, that was the game. Remember, did you ever play when you were a kid, hide and seek? It was interesting when you lived in an apartment complex with the other kids when I was young. All right, it's time for our last lab. I'm sad. Semester's almost gone, and we're going to be going our separate paths. But don't forget, you can always email me and say hello. And with Zoom, I can always set up a Zoom meeting. So you're never a Zoom meeting away from Dr. White, whatever that means. All right, last lab. This lab deals with standardization of a sodium hydroxide solution. It turns out in both research labs, academic labs, and industrial labs, especially quality control labs at chemical plants, it's very important to have on hand standardized sodium hydroxide solutions. What do I mean by standardized? It means you know very accurately the molarity of a solution that you make. And at one lab I managed, we used to make gallon quantities of it because we use that much for other things, like titrating HCl solutions to make sure what they are. So the question is, if you make a molar solution of sodium hydroxide is a solid, you weigh out a certain amount of sodium hydroxide, you put it in a volumetric flask, you put in water, dissolve it, then fill it up. So it's say 1 liter, is it that amount? Well, you don't take a gamble and say, yeah, I did it right. You analyze it. And that's called standardization. And how do you standardize it? With a monoprotic solid acid called KHP, which is not what I want. All right, everybody see standardization is thank you. All right, so the universally used standard monoprotic acid for standardizing sodium hydroxide is KHP. Everybody who's a chemist, they don't know what KHP stands for. They're lying to you because they're not a chemist. It stands for the compound potassium hydroxide, hydrogen phthalate. And KHP has one acidic proton. And KHP will react with sodium hydroxide to give us salt and water. And therefore, you do a titration. And when you do a titration, you use a pH indicator. Remember, a pH indicator changes color at the endpoint. And at the endpoint, also called neutralization, when the pH indicator changes color, the following is true. Equation 1. Moles of KHP equals moles of sodium hydroxide. Just like you learned for titrations, moles of acid equal moles of base. Well, KHP is our acid, sodium hydroxide is our base. Now, we just practiced, moles of any compound equals the grams of that compound divided times 1 mole over the molecular weight. And for KHP, for this lab, 3 significant figures is enough. The moles of KHP would be grams of KHP divided by 204 grams which is the molecular weight of KHP. You can look it up, which means moles, you can calculate the moles of KHP used right here, and then you'll titrate it with milliliters of sodium hydroxide. And remember from titration, moles of something, we have a concentration of solution is milliliters times moles per 1,000 milliliters. That's molarity. Now, I did it real quick. If you solve for molarity, you get moles of KHP times 1,000 equals milliliters. for those of you who must know, I'll do it. Dr. White is having an awful whiteboard day. And what I'm doing is showing you how I got the equation 3, in case anybody was interested. Hopefully, maybe one of you are. What do I want alone on this side? This, because it's moles per 1,000 milliliters, which is molarity. So once I calculate this, this will also be molarity. Well, if I want to get rid of the milliliters of sodium hydroxide, I divide both sides by milliliters. And I did that. Now, if I want to get rid of 1,000, how do you get rid of 1 over x? Well, if you multiply it by x, that equals 1 times x over x, and it's gone. So that's why, and I've stayed away from doing that this semester. I'll put that on top, multiply this on top, so I've got to multiply this side on top. This cancels out, this cancels out, and what does that leave me? A mess. This you don't have to calculate right down. I've already done this work for you, but you can always come back and look at the video if you want to. And this means 1,000 milliliters times moles KHP divided by the milliliters NaOH equals moles of sodium hydroxide, which you're going to calculate because you're going to find out how many milliliters of NaOH is needed to neutralize the moles of KHP. Now, notice this is moles per 1,000 milliliters, which also makes this number the molarity. And that's how you do it. Now, one thing I should warn you about KHP. KHP is very hygroscopic. That means it likes to absorb water. Speaking about water, I need a drink. It absorbs this stuff. And what do? Well, first of all, whenever you're using KHP, you always put it in a hot oven in the laboratory. They have ovens to do this, to heat it for a while to drive off the water. I like that. And then what you do is you take it out and use tongs because it's in a container hot, and you put it in what's called a desiccator. And a desiccator is this giant jar that has in the bottom a chemical that absorbs moisture. So it's dry in there and you let it cool off. Then right before you use it, you take it out of the jar, desiccator. Let me see if I can find a picture of desiccator for you. That's not what I want. Does everybody see on the screen the desiccator? Notice it's got that white plate at the bottom inside, and that underneath it, you put the chemical. It's called, the commercial version, it's called dry right. And It's actually colored. It's a blue color. If it's pink, that means you got to take it out and put it in an oven to get off the moisture. And this has a heavy glass lid, and there's vacuum grease here that keeps this totally sealed from the air outside. And that's where you can let it cool and dry off stuff. So using dry KHP, when you do it, you can find the molarity of your sodium hydroxide solution very accurately. And that's what you'll be doing today, using equations 2 and 3 with the data from this titration will allow you to accurately determine the molarity of a sodium hydroxide solution. Now, whenever you're doing a titration in the real world or in a lab class like ours, you always do it in duplicate. You do it twice. Why? To make sure you didn't make a mistake, because you're trying to find something accurately. And what you should do, if you did it right, the first run and the second run, the numbers should be the same. You should get the same molarity. If not, you better go back to the drawing board. You made a mistake. So I'm going to give you that opportunity to do that too. Now, if you notice, I have the procedure here. And I'm going to go through this in Beyond Lab Z. Important thing here, I'll show you how to do step 9. And the other one, step 14, I had some troubles with initially, and I realized you got to move the eyedropper to the beaker until it snaps in place, and I'll show it to you. And you'll do this, exit the lab and enter it again to redo steps 3 through 17. Now, when you're doing it, you'll weigh out grams of KHP. And then you can calculate using equation 2 the moles for each run. You'll have your initial burette volume, you did that last lab that you're handing in today, and a final. And I hope you all know what's the volume. That's the difference of these two numbers of NaOH, your milliliters. And then to calculate molarity, you use sodium hydroxide. A molarity of sodium hydroxide, you use equation 3. So hopefully I made it somewhat painless for you. And now let's go to Beyond Lab Z. Does everybody see titrations on your screen? All right, first thing you're going to do, in the lower left, like you did last week, click on acid-base chemistry where it says worksheets. Then scroll down. Near the bottom, see where it says acid-base standardization? Click on that. Does everybody see the lab? First thing you got to do is get a beaker and put it over here. Ooh, we've got sound today. Can you hear that sound too? And now close the drawer so you don't bang into it and click on the balance. Take the lid off here, put the weighing paper in here, move this, click on tare, zero it. Now, here's a trick I found out the hard way. It's called reading the instructions. Dr. White has a bad habit of not reading instructions because I figure I can figure anything out, but sometimes it helps to read the instructions. And here, what you do is pick up the spatula and see on the label of the bottle, they have 5 different things, levels of KHP. Go to the bottom one and see how it fills it up. Then you got to go here until it snaps in place, and then you do that a second time. Come down to the bottom one, come over here, see how it's snapped in place, let go, and now record this number, 1.977 9797. Record all these, that would be, 5 significant figures. Now you pick this up and you move it over here to the beaker. Ta-da! And now where it says zoom out, you zoom out. Now you take the beaker, and before I move it, you want to use this tap, the one that's curved, the one that's not with two knobs. And we have the same thing in a sink, except the knobs are on this side because you're going to be standing over here. That's tap water. I call it city water because I worked in industry and that's what we call it. In the curved one here with the white tip, that's deionized water, which we always use in a lab. So you'll take it under here. And no, I don't want to do that. Oh, come on, get under there. There you go. Hope I didn't dump it. And we'll put it here. Now, this is the trickiest part of the lab. See the second bottle from the second row, second over, is phenolphthalein. You'll take it. Now, here's the trick. You'll hold it here. See how it's snapped up? If it doesn't do that, you're not putting any in there. And you let go. Now, your burette already has the sodium hydroxide. Notice on here, this is unknown number 8. And I'll call this, we're starting at 0.00 milliliters. That's our initial volume. And now, if you want, we got an indicator, but I like it. I'll put my pH probe, which shows over here, and you got a graph. You don't need to use it, but it's fun. And now I'm going to add it. Now, you'll add until you see a color change, and you stop. And you can shotgun it in. You can do a first one just to do it, and I hope I didn't dump it in this graduated cylinder. I will find out. Now, the nice thing about the plot is you can't see it if it's over there. Let me do something. Now you can see the plot. I'm doing it fast so you don't have to spend all morning watching me do this. If you notice, the graph is starting to edge up, which tells me I'm near my endpoint. Stop. Everybody see how I got that? Now, I've done over a thousand or more titrations, so I know how to shotgun it. And you might want it a first time, do it quickly, but you're going to do more than 30 milliliters, I'll bet, if you put the right amount, about 2 grams in there. And this is their endpoint. And now I can look at the burette. Everybody see this right here? Now, this number is 34. Above here would be 33. And each one of these little lines is 1/10 of a milliliter. So this would be 33.9, 33.8. Notice it's in between 33.9 8 and 33.9, because you look at the bottom of the U, the meniscus, so I'd call that 33.85. And guess what? You're done. Now, to do the second run, the quickest way is hit exit, go back to acid-base titrations, and you put the beaker in there and repeat what I just did. And that's today's lab. And like I said, at one lab I managed, at least 3 times a week, we'd make about a gallon of sodium hydroxide standardized molar solution. And one of the chemists working for me would do this type of standardization titration and do it in duplicate. Then come and show me the numbers. I said, all right, that's good accuracy. You can put that on the label of this gallon bottle that everybody used for other titrations. Now, notice I have questions. And Dr. White did a good one. Look at number 5. Everybody see number 5 on your screen? KHP can absorb water if it's not kept in a desiccator, a container used to dry things, keep things dry, and then put it in an oven before using. Explain what would happen to the numerical, notice I underlined it, value of your sodium hydroxide solution results if you had wet KHP. Does everybody know what wet means? That means there's water in it. Now you do know what wet is. And that's a good, I'm so proud of that question in real life. That's an important thing to consider. And with that, that's our final lab. And I'm done for today. Uh, for those of you, well, none of you have lab tomorrow, uh, rain, rain freeze. With that, I'll see you all Monday. Remember, by Sunday, 1 p.m., I'm shooting for Saturday. Hopefully, I'll have the scores for test number 4 in Blackboard. By Sunday, 1 p.m., I will also mail out to you the individual points for each question or part of a question you answer. Also, I hope by Sunday evening in Blackboard, I will have every lab that you have handed in graded. Remember, hand in the lab that's due today. Today's lab is due next Thursday. And with that, I'll see you on Monday. Bye. Gang gesund. Be healthy. Have a nice couple days.